Hello and welcome to another episode of Chemistry. Today we're going to actually talk about calorimetry. So what we're actually going to do is talk about what a calorimeter is, calculating calibration factors, and then how we use that to calculate enthalpy or heat of combustion or heat of... What does a calorimeter do? Now, if you look at the actual diagram here, you can see this is a very, very basic calorimeter. In fact, it almost just looks like a styrofoam cup with a lid on it. But the elements are fundamentally this. You've got this sort of covered, insulated container. And that insulation is actually really important. You've got a stirrer generally, so you want to stir the content of what's in the calorimeter, but also you have a thermometer, and the whole point of the thermometer is actually to measure temperature change. So as you can imagine, a calorimeter is used to measure heat changes, specifically using the changes in temperature, so that we can see what's happening in a reaction. And then using that information, we can actually calculate enthalpy. So if the temperature goes up, that means that energy is being released into that environment. In here, we're talking about this liquid here. If there's an increase in temperature, energy is being released into that liquid. As a result, that pretty much says to us, hey, it's an exothermic reaction. If the temperature decreases, the energy is being taken in from the environment into the reaction. And as a result of that, the temperature goes down, so it's an endothermic reaction. As I said before, insulation is a really important part of calorimetry because if you think about it, if you're measuring the temperature, you want to make sure that all of the energy that's released into the solution that we saw is kept in the solution. You don't want any of that energy to seep through the calorimeter into the outer environment. And so sometimes some calorimeters are better than others. And in fact, even if you look at the same type of calorimeter, it varies. So if I picked up a calorimeter from our trolley at school and you picked up the same type of calorimeter from the same trolley, chances are the ability to keep the energy in, the insulation between yours and my calorimeter is still going to be different. And so as a result of that, we have to calculate something called calibration factor. Now, calibration factor really just takes into consideration, hey, maybe some calorimeters are better insulators than others. Some will result in more energy loss than others, but that's okay. We can take that into account in our calculations. So a calibration factor really just says, hey, for this particular calorimeter that you're looking at, it tells you how much energy is required to change the temperature of the contents in the calorimeter itself by 1 degree, specific to that calorimeter. Now, the reason why I left this empty box is I want you to help me generate the formula for this. So we're saying that the calibration factor is about how much temperature, so the temperature change, how much energy is required to change the temperature by 1 degree. How much energy is required? Now, in this sense, the energy required is actually going to be measured in joules. How much energy is required to change the temperature by 1 degree? So if we have those units, we can actually have a think about what do those units actually mean and how do we use that to generate a formula or to generate a mathematical explanation for it. You know that joules here, as we already said, that represents energy. This here represents temperature. So specifically the change in temperature. So if you were to generate a formula from that, you'll say, cool, easy. Calibration factor is energy in joules over the change in temperature. And the reason why I use a change in temperature value is when I do the division, it will calculate per degree Celsius. The great thing is you don't have to memorize it. So if you're doing VC chemistry, this is actually in the data book for you. And as we established here, it's energy, usually measured in joules, divided by the delta T, usually in degrees Celsius, but it doesn't have to be. It just means that you've got a change in temperature. So before you do any experiment, you have to calibrate it first. You have to figure out, in this particular calorimeter, how much energy is required to increase the temperature by 1 degree. Once you've done the calibration and you've established what the calibration factor is, then you do your actual experiment. So please don't get these mixed around. I see too many students thinking that they're both the same thing. Calibrate first, figure out the calibration factor, and then do the experiment. Two separate, I wouldn't even call it experiments, two separate processes, two separate procedures. Let's look at it diagrammatically. The first thing what we want to do is how much energy is required to change the temperature. So really, the first thing we want to do is to use this information to calculate the calibration factor. Now, because you're usually doing it before an experiment, you have to make sure the conditions are the same when you calibrate it versus when you do it for experiments. So for example, if you're going to have, 100 mils of solution in your experiment, you calibrate it with 100 mils of water because water is generally what we use to actually make solutions. So you just, as much as you can, make the conditions for both the same. So for VC Chem, they're really asking for you to understand solution calorimetry, which is you have some sort of solution in the calorimeter, you want to measure energy changes from that. Usually it's sort of, when we're talking about enthalpy, if we're talking specifically, it could be heat of solution or heat of neutralization. Now, neutralization is like your acid and base reaction that you learnt about in year 11. So, as I mentioned before, the volume you use to calibrate is the same as the volume of the reaction, the total reaction. So again, if you have a look at my really incredible drawing, you've got your stirrer, you've got your thermometer, but you'll notice here you've got something really interesting. That is the electrical heater. Now, this is the energy source. Not only is it the energy source for you to calibrate, it's actually the energy source required for the reaction. Because as you know, we need energy to break bonds and do all that sort of stuff. This provides that energy in order for the reaction to occur. Get to the activation energy, allow for a reaction to happen. And because we're using an electrical energy source, yes, to calculate the calibration factor, it's still this. However, the way in which we calculate energy is slightly different because of the values that we have are going to be electrical energy. So what does that look like? Ta-da! The data book has come up with the goods once again. So here, VIT just means energy, where V is volts, I is current, and T is time, but the time is in seconds. Current is in amps, and volts is in that. Cool. Right, let's do an example. So say you're going to do an experiment, and what you want to do is you want to calibrate it first. This much current, 200 seconds, and the voltage that you're applying to that actual experiment or that calibration is 4 volts. Now, given that the temperature is increased by 5 degrees, what we have to do is calculate the calibration factor. All we need to do is this. As we said, energy over delta T. Now, delta T we've got because we've been told that it increases by 5 degrees. But the energy we have to calculate. And luckily for us, we've got the right values to do that. So we've got voltage here, we've got current, and we've got time as well. So I just multiply the numbers. That's 200. So here, 400. What does that mean? That means for this particular calorimeter, it takes 400 joules to increase the temperature by 1 degree. So that's calculating calibration factors. See, and then thinking about what we can do with it later on. But before we do that, during that calibration phase, what we want to do is we want to make sure, as best we can, the calorimeter that we're using is really well insulated, right? So a way in which to do that, so we've calculated a calibration curve, but we can use that process to actually do something called, to draw something called a calibration curve. Now, you can see with the curve, there's a point, and so there's a temperature here, so say 15 degrees, it starts off with 15 degrees. You turn on your electrical current. You leave it on for a little while, and then you turn it off. And as you can see, there's a delta T here, the temperature change as a result of that. Once you've turned it off at about 19 seconds, you want to see what happens afterwards. Now, really, really nice result here is that you have a flat line, which means that as time goes on, you're really not losing any energy. That means that you've got a really well insulated calorimeter because you're not losing energy. You can imagine on the flip side, for a not so well insulated calorimeter, turn it on, turn it off, but then as soon as you turn it off, it almost starts to just decrease in temperature. Why? Because it almost leaks energy out of the calorimeter, so it's not very well insulated. So when that is the case, what you want to do is you actually want to extrapolate. You go back. So when you get to that point when you've turned on the current, that's the delta T that you take, not the delta T of this, because you're not sure, it's not accurate, it's not well insulated. So really, look at that, what happened there? So really, who cares about a calibration factor? Well, now that we know how much energy it takes to change the temperature by 1 degree in that calorimeter, and we've also been able to figure out whether it's well insulated or not, we can use that information to figure out the energy changes when we do a reaction for real. So this is the second part. If we rearrange the formula, what we can actually do is to calculate the energy released from the reaction. So if we think about this is calibration factor, energy over delta T. If we rearrange this, we can actually find the energy released by doing this. Interesting. Once we find the energy released, we can attribute it to whatever the reaction is and find out the enthalpy. So say, for example, you've got this. Solution calorimetry, 50 mils of 1 molar sodium hydroxide, 50 mils of 1 molar hydrochloric acid. So literally, you're adding those two together. It's a neutralization reaction. You've got your acid, your base, and you've got your acid. The great thing is both of them are starting at the same temperature. Once they've mixed, as a result of the reaction, you've got a temperature change from 22.5 to 28.7. And we've been told actually that the calibration factor is 385 joules per degree. That means it takes 385 joules to increase the temperature of the contents of this calorimeter. So that's both 50, so that's 100 mils by 1 degree. So the first thing is, let's write a balanced equation for the reaction. So making sure that you've got the states here. Now in a neutralization reaction like this, you get a salt and you also get water. So I'm happy that it's a 1-to-1. So everything is a 1-to-1 ratio, which is great. The next question says, let's use this information to actually calculate the heat energy released in this reaction. Remembering that we can actually figure out the energy released into the system, that means that really the energy released into the system caused the temperature change. So by doing that and knowing that we've got the calibration factor, it's this. And the temperature change is... So the energy that got released as a result of this reaction is... So as a result of this reaction, we know that over 2,300 joules was actually released. The last thing is, so let's just write that value again. So 2387. Knowing that we released 2387 joules as a result of this reaction, we can figure out the heat of neutralization. The heat of neutralization is the same as saying pretty much like delta H, which is what you've always known. So what we have to do now is to figure out, well, what's the delta H of this reaction? Remember that to calculate delta H, so usually we express it in kilojoules per mole. And that gives you what you need, energy, and you also need mole. Now, the great thing is we have energy. We've been able to calculate that. And so the next bit of information that we need is the number of mole. So given that our reaction looks like this, and I'm not going to put the states, I'm just showing you for reference. The great thing is everything's a 1-to-1 ratio. So it doesn't matter which mole of substance you're going to use. You can use it both for sodium hydroxide, you can use hydrochloric acid. And luckily for us, they're both the same value. So since I already have E, what I need to do is I need to calculate the number of mole. So before I can use this, I have to first calculate the number of mole, and I'm just going to go for sodium hydroxide. N equals C times V. And remember that V is going to be in liters, so that makes it 0.05 mole. So what that means is, by using 0.05 mole of sodium hydroxide, and also, by the way, hydrochloric acid, I'm able to release this much energy. So what I can do there is to use this information to actually calculate the delta H. So the energy, I'm going to convert that to kilojoules. So going from that many joules to kilojoules, divide that by 0.05. So the answer I should get here, 47.7 kilojoules per mole. So we've just been able to use calibration factor, calorimetry to actually figure out the enthalpy of a neutralization reaction. What about another one? Oh, sorry about this. So instead of a neutralization reaction, what if you've got something where there's a substance that dissolves in a solution? So you've got ammonium nitrate, you dissolve it in water, the initial temperature was this, the final temperature is actually in the reverse. So what we've done is we've actually lost energy. What we need to do is we need to calculate the enthalpy change for this process given in kilojoules per mole. Now remember, since it's in kilojoules per mole, they kind of tell you what you need to do in your reaction. So enthalpy here, again, is energy over mole. Really what I need to do is to have both pieces of information, both energy and mole. Unfortunately, I don't have either at the moment. Right? All of these values can lead me to those, but I don't have any. So what I'm going to do is I'm going to do this one at a time. First thing I want to do is I want to figure out, well, how much energy was released when the dissolving process occurred. I can figure that out because I know that for every degree change, it was 420 joules per degrees. Now, interestingly enough, the temperature change is negative. What that means is energy is absorbed, which means that this is going to be an endothermic reaction. And that will give you the direction you need for your value. Is it positive or is it negative? So let's do this. Energy, that's going to be calibration factor times delta T. I've got this. Now delta T is negative, so what we can do is we can make it negative. So it started off with, so the difference is this. We can keep it negative, it's totally fine. So I've got the energy value here. The next thing I'm going to do is now I've got energy, now I'm going to figure out the number of mole. So let's do 2. Number of mole of my, what did I say, an ammonium nitrate. Now, how do I know the number of mole of ammonium nitrate? Luckily for us, I've got the mass of ammonium nitrate that was used. So let's use that to calculate mole. When I do that conversion, I know that that was 0.05 mole. So if I use 0.05 mole, I had to absorb 1,176 joules of energy. Cool, now I can use that information to calculate delta H because I've got both mole and energy. Now the energy, I'm going to convert this value, energy value, 176 divided by 0.05. Now, this 23.5 kilojoules per mole, this is going to be important. Am I going to put a negative sign or a positive sign? Now, we said at the start that it's an endothermic reaction, and that to show endothermic reactions, I've actually got to use a positive value because energy is being absorbed. Therefore, I just finish it off saying, hey, it's a positive value. Cool. Let's summarize what we've learnt right now. Calorimeters, what they do is they measure energy changes. We also know that calibration factors tell you information about how much energy is required or decrease the temperature by a degree. And we can use calibration graphs to actually try and figure out whether or not something is really well insulated or not. What I probably should have said at the end of this is you can actually calculate delta H from this. I don't know what happened there, but let's redo that. My bad. Nice one. Cool. Thank you so much for hanging out with me today. I hope that was useful. I hope you learned something new. Always remember, no matter what anybody says, you can. Bye.